Okay, let's spend a few moments thinking about measures of association, also called measures of correlation. We're talking about how one variable is associated or correlated or related to another variable. And typically we're thinking of numeric variables. There are two measures that we use when we think about this, and these are the covariance and the correlation, and both of these give you an indication of the strength and direction of linear relationships between two variables. But as we'll see, one of them is a bit more useful for us than the other. The covariance is calculated using this formula, and just to step you through what this indicates, it really follows the definition of a covariance as the average of the product of the deviations of the two variables x and y. With the one caveat that when we're talking about samples, as this formula indicates, the average is the sum of those products divided by not n, but n minus 1. Okay, so we have our variable x and we have x bar, the average value of x. We have y and we have y bar, the average value of y. And for every x value, we subtract the average x value, and that becomes the deviation of x. Similarly, we have the deviation of y. And for every pair of observations, x and y, we take the product of those two deviations. We sum those products across every combination, every pair of x and y values, and divide by n minus 1 in the case of if we're treating this as a sample, and that gives us our covariance. If we were specifically designating this as a population, we would divide, of course, by n, as opposed to n minus 1. So that gives us our covariance. And again, we'll see how we can calculate these in Excel. But it measures the combined deviations. I want to show you the formula because I want you to understand what it is that it's doing and how it gives us some indication about the relationship between these two variables, and particularly the direction of the relationship. Is it a positive relationship or a negative relationship? Are the two variables moving together? When x increases, does y also increase? When x tends to be low compared to its mean, is y also low compared to its mean? Or by chance, are they moving in the opposite direction? Relatively higher x values leading to relatively lower y values. And we'll see how this emerges from this mathematical expression, particularly from these products of the deviations of x and x bar. The sign of that product is what's going to give us indicate the direction of the relationship. So think about a scatter plot of x versus y. And in this case, I've got a collection of points, scatter points here, indicating salary on the y-axis and some measure of culture, some numeric measure of culture on the x-axis. And these points are clustered around on the paper, and we want to get a sense for what the relationship might be. And what I'll do is start out by drawing a line, or just imagining a line at a point on the x-axis that represents the average x value for all of these points. So this would be the average of each of these x values. And I'm going to do the same thing on the y-axis and come up with an imaginary line here representing the average of the salary values for all of these points. Well, as we start looking at the location of all of these points relative to the average x and y values, we'll see how the direction of the relationship emerges from this formula. Imagine point 1 that I've shown here. Okay, its x value, we'll go back, its x value would fall somewhere here on the x-axis, and the x deviation would be positive because the x value of point 1 is greater than x bar. So this is a positive deviation. What about its y value? Well, its y value would fall somewhere here on the y-axis, and its y deviation would also be positive. So when you look at the product of the deviations of the x and y values for point 1, that product is going to have a positive sign. What about point 2 down here? Well, its x deviation is negative because its x value is below x bar, and its y deviation is also negative. So in product, those two deviations are again going to have a positive contribution to the overall covariance. And we can contrast that with point 3, which has a negative x deviation, but a positive y deviation. And this point is going to have a product of its deviations that is negative. And similarly for point 4, because it has a positive x deviation and a negative y deviation. So in product, point 4 is going to have a negative contribution to the covariance. So what happens as we look at all the points in this data set is we're essentially summing all the positive and negative contributions from these products. So if there are a lot of points that fall in the upper right or lower left quadrants compared to the lower right and upper left, then in general the contribution up here is going to be positive, much more positive than negative. And therefore, when we take the average, we're going to end up with a number that is positive. By contrast, if, unlike what's shown here, we had many more points that fell in the upper left and lower right quadrants and relatively fewer that fell in the upper right and lower left quadrants, then we'd have an overall negative average value for this covariance. And that's how the covariance actually carries and illustrates the direction of the relationship. And I just want to show you this in a bit more of a, let's call it a live format here. And I'm going to bring into our screen in a slightly messy way an applet that shows you the a scatter plot of points and the 4 quadrants I just spoke about. And here you can see the number of points in each quadrant: 5 in the upper left, 6 in the lower left, 4 in the lower right, 5 in the upper right. And I'm just going to play around here with the scatter of these points. So I'm going to move some points around here. And what I'm doing is I'm moving it towards a more positive orientation, where there's an imaginary line here that the points are clustered around that has a positive slope. And as you can see from the counts, I now have many more points in the upper right and lower left quadrants, and my R value, as it's shown here, which is my correlation coefficient, has an overall positive value. If I were to pull things in the opposite direction, my R value, my correlation coefficient, takes on a negative value overall. Okay, now we'll see in a moment how the correlation coefficient emerges from the covariance, but it's based on the same idea of the this average value of these products of these deviations. All right, well, what happens in covariance? We can find the covariance in Excel if we have 2 columns or arrays of values. We can use this formula, equals covar, and then in parentheses we select our 2 columns of data separated by a comma. The units of covariance, as you might imagine, are a little messy because it's going to be the product of the units of each of the 2 variables. The other thing that gets messy with covariance is that the magnitude tends to track with the scale of each variable. So it's very hard to extract the meaning from that, the magnitude of the covariance number. And as a way to resolve both of those issues, we've come up with the correlation coefficient. And all that does is take the covariance and divide it by the product of the standard deviations of the 2 variables, x and y. And if you think what that does to the scale is you're looking at the product of these 2 deviations and dividing it by the average deviation for x and the average deviation for y. So we're really bringing everything down into a scale of the deviation, of a typical deviation for x or y. And it also reduces the units, by the way, because the standard deviation of x is going to have its original the units of x, and the standard deviation of y will carry the units of y, so they'll cancel out completely, and as a result, correlation coefficient has no units, or it's dimensionless, as they say in mathematics. The other thing that happens, again, because the scale is reduced, is that the value, the maximum magnitude you can have for correlation coefficient is going to be a value of 1. And because the sign tracks with the direction of the relationship, the overall range is going to be from -1 to +1. This now is much more easy for us to interpret, both in terms of the units as well as the fact that the scale, the magnitude of this correlation coefficient, can only go from 0 to 1 regardless of what the magnitudes are of any of these original units. So it helps us be able to say in absolute terms something very concrete about the relationship between the two variables. In Excel, if we want to get that correlation coefficient, the formula is CORREL, C-O-R-R-E-L, and then our two arrays of values for the x and y variables separated by a comma. So we can graph a relationship with a scatter plot, and we can understand what's happening based on what we're visually seeing. But the correlation coefficient can give us a much more objective measure. Here are some basic properties that apply to correlation coefficients and covariances. And this may make sense. A correlation between x and y is the same as a correlation between y and x. Same thing as saying it doesn't matter which of the two variables we actually put on our x or y axes, the correlation, the relationship between them will be the same. The covariance between a variable and itself is going to just reduce to the variance of the variable. So if we think back to the variance formula, if instead of having x and y, I just have x and x, essentially, it's the deviation squared, and the definition ends up being exactly the definition of the variance of that variable x. And the other interesting point is that the correlation between a variable and itself is always going to be a +1. That makes sense. If you took a variable and plotted it on its twice, once on the x-axis, once on the y-axis, all the points would fall along a straight line that had a positive slope. All right, so that gives us some basics on correlation and the covariance that the correlation is derived from, and we'll take a look at an example with some numbers to it.